Come back. Today I will at first discuss some beautiful topic. This time is a study time because all exam had announced. So today I will tell you some beautiful topic. How you will begin your day. Because what you do in the first few hours of the day is going to affect your whole day. The better way is try to wake up early and try to sleep in early night, because in morning whole earth has positive energy, and I personally wake 5 o'clock. After waking, at first keep your book properly and clean your study room, and after freshing, do some exercise and do meditation also. And be thankful for your life and for everything. Come back. Today I will discuss some question of maximal ideal, which is very important for any competitive exam. Let's see the question. First question is, consider the set M equal to f of x such that f of half equal to 0. Then show that this set M is a maximal ideal of the ring. At first check, is it subring? Here the set is look like f of x such that f of half equal to 0. Consider two functions f of 1 and f of 2 which belongs to this member, such that f of 1 half equal to 0 and f of 2 half equal to 0. Then f1 minus f2 half equal to, we can write it as easily by the property of the function f of f1 half minus f2 half, and since here given f1 half equal to 0 and f2 half equal to 0, therefore put this value, then this value equal to 0. And from this line, we can tell easily f1 minus f2x belongs to the set M. Okay? That means M is obviously be a subring. Okay? Well, since the set is subring, now I will check is the set is ideal. Consider a function f belongs to M and small r belongs to the ring R. Then f of half times r half, this value would be, since given f belongs to the set M, obviously this value equal to 0 times r half. That means this is equal to 0. That means from this line, we can tell easily f of x times r of x belongs to M. That means obviously M is an ideal of the ring R. Okay? I have got M is an ideal of the ring R. Now I will prove M is a maximal ideal of the ring R. And actually this is our goal. For this, we have to prove there is no proper ideal R which is properly contained in M. Let consider capital U be any ideal which properly contained in the set capital M. If we see the picture, this is the ring R and this is considered U be any ideal, which is properly contained in the set M. From this picture, we can tell easily there exists an element Gx belongs to U such that G of half not equal to 0. That means that from this line we can tell G of half equal to just a point C, which is not equal to 0. Take a new function Hx as like G of x minus C. Then if we put the value h of half, then this is equal to G of half minus C, and since G of half equal to C, then this value equal to C minus C equal to 0. That means h half equal to 0. Okay? And since h half equal to 0, therefore we can tell easily Hx belongs to the set M, and which is contained in the set capital U. And also Gx belongs to the set U. Therefore, since I have got Hx belongs to U and Gx belongs to U, then obviously their subtraction means Gx minus Hx obviously belongs to U. That means Gx minus Hx belongs to U, and put the value Hx, then this would be Gx minus C, which would be belongs to U. That means from this line we can tell easily C belongs to U. And since C is member of the ring R, obviously their inverse would be belongs to U. That implies C times C inverse belongs to the set U. From this line, I have got 1 belongs to U. Since U is an ideal and 1 belongs to U, therefore U is nothing but the whole ring R. That means from this line we can tell easily there exists no proper ideal of the ring R which is properly contained in the set M. That means the set M is maximal ideal. There is no proper ideal which is contained in M. Therefore, our proof has done this set is a maximal ideal of the ring R. Similarly, we can prove the ideal f belongs to C01 such that f of a equal to 0 where a belongs to closed interval 0, 1 and a is a single point. Obviously, this set I be a maximal ideal of C01. Similar proof, just try it on self. And this type of proof is very important for any competitive exam. If we consider the set I equal to f belongs to C01 such that f of 0 equal to f of 1 equal to 0, now my question, is it maximal ideal of C01? No. Because if we consider I equal to f belongs to C01 such that f of 0 equal to f of 1 equal to 0, now if we consider other set I dash such that f belongs to C01 and f of 1 equal to 0, obviously I contain the set I dash which is subset of the set C01. C01 means set of all continuous function which is defined on 0, 1. Therefore, from this line, we can tell the set I is not maximal ideal of the C01. Okay? Are you getting? Here, this is true because I not equal to I dash. So this type of set is not a maximal ideal. But when 0 only one single point, so obviously this set will be maximal ideal. I will discuss one example of CSIR net which had come in June 2019 exam. This question is very important. Here notice the question is x equal to 0, 1, and notice here the interval is open interval, be an open unit interval, and C of XR be the ring of continuous function from x to R for any x here belongs to open interval 0, 1. Now consider a set Ix such that f belongs to C of XR such that f of x equal to 0. Then which of the following are true? Option 1, Ix is a prime ideal. Option 2, Ix is a maximal ideal. Option 3, every maximal ideal of C of XR is equal to Ix for some x belongs to capital X. And option 4, C of XR is an integral domain. Here notice the set is f belongs to C of XR such that f of x equal to 0. I have seen in few minutes ago this type of set obviously maximal ideal, but in before example the interval was closed and bounded interval, but here open interval. This is maximal ideal is obviously true in this interval also, same like before the proof. That means option 2 is obviously right option, and option 1 Ix is prime ideal. We all of us know in a commutative ring with unity every maximal ideal is a prime ideal. So since C of 0, 1 is commutative ring with unity, so obviously this set is prime ideal because this is the maximal ideal. And option 3 is very interesting. Here every maximal ideal of C of XR is equal to Ix. Ix means this set for some x belongs to x. What is the set again? Here x belongs to open interval 0, 1 and Ix equal to f belongs to C of XR such that f of x equal to 0. Now I will say new type of function, compactly supported function. Notice the function gx equal to x square minus 1 over 4 when x belongs to close interval 0, open interval half, and otherwise the value of the function is 0. Here notice the closure of the set close 0 open half equal to close 0 half. That means the function is not equal to 0 domain whose closure is not equal to 0, and otherwise the function is the value of the function is 0. So this function is compactly supported function. That means those functions are called compactly supported function if the function is not equal to 0 on the domain whose closure is compact. Consider a set J. This set is such that f belongs to C of XR such that f is compactly supported. Now consider y belongs to the set x, which is open interval 0, 1, such that y equal to 0. That means this set belongs to our given set I. Now consider an arbitrary function g from j such that g of y not equal to 0 where y belongs to ny. That means ny is compactly supported set, and otherwise the value of the g of function is 0. That means from this condition we can tell easily g does not belongs to iy, since I have taken here arbitrary y. So we can tell easily j does not belongs to, that means belongs to iy, that means j does not contains iy. That means the set j is maximal ideal because there is no bigger ideal. So every maximal ideal of C of XR is equal to Ix for some x belongs to x. This is the wrong option. And option 4, C of XR is an integral domain. Consider a new type of function f of x equal to 0 for 0 less than x less than equal to alpha, and x minus alpha for alpha less than x less than 1. That means this graph would be this type of function. This is the fx, and g of x equal to x minus alpha for 0 less than x less than equal to alpha, and 0 for alpha less than x less than 1. That means this graph would be such type of function. This type of function is called g of x. And notice here f of x and g of x both non-zero function, but their product would be 0. That means C of XR is not integral domain because this is contain 0 divisor, and this is true for uncountable number of alpha. Are you getting? Well, so option 4 also wrong option. Only option 1 and option 2 are right option. Okay? Yeah, I will stop here, and in my next video I will discuss this topic elaborately also, because this topic is very important for any competitive exam. See you soon. Stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.